Well, I think first and foremost, it's an excellent way of integrating seismic, well logs, and biostratigraphy. That I don't know of any other approach that can do that quite as nicely. It's based on chronostratigraphy, which requires biostratigraphy. It makes use of parasequences and things you can recognize at the well log scale. Then it also makes use of seismic reflection data, which is really important to seismic facies analysis, stratal terminations, and so on.
Well, it allows you to take disparate observations and put them into context. So it essentially provides the framework or the context that accommodates disparate or seemingly disparate observations.
Every geologist will have an opinion about what the stratigraphy is, but a lot of times what we really need is a methodology so that we can get away from opinion and get towards a relatively robust and defensible, non-opinion-based stratigraphic frameworks.
When I joined Exxon and got exposed to these concepts, like, this actually makes sense. There is predictability. It isn't all random. That there actually are things that you can actually, from looking at different data sets, predicts in other parts of the basin. And things make sense. It isn't all random. There's actually an organization to geology. And that's something I really just found very enlightening and really changed the way I approached how I did stratigraphy and such.
But sequence stratigraphy and the methodology of sequence stratigraphy, asked me to look at surfaces and the processes that were active and going on in different types of surfaces. It caused me to look at a core and see all of these different types of surfaces and say, what's generated in these huge erosional surfaces, often deep marine systems, right? Is this a mass failure? Is it a current-driven erosional surface? Is it a turbidite-driven erosional surface? So it made me question what were the processes that were active that were generating the stratigraphy around me.
I think that one of the ways I viewed sequence stratigraphy is to make you think about the whole system, what's responding in the basin relative to what's happening up on the platform, and vice versa. And that scale requires you to start pulling in broader data sets so that you can see, all right, okay, if we have a karst surface up on the platform, there must be some sort of response out in the basin, and we need to go look at least to see if that's a valid hypothesis, test that hypothesis, and see what's out there as a low stand. So it forced us to look along these timelines, and connect the dots, from the shelf into the basin, which I've always viewed as one of the powerful aspects of sequence stratigraphy.
Well, for me, it's a method to take apart the architecture of a reservoir, so to speak, understand its distribution and the facies that are within that reservoir.
And basically it's just doing fundamental play analysis, but do it within that strat framework. So it helped understand timing of structure, migration, maturation, and so on. So it was, I'd say, any basin that we looked at in the 80s and into the 90s, that was clearly what we did.
I think the systematic analysis, rather than just going in and doing a structural interpretation and finding a structure that you can market to management and get drilled, you were able to go in and assess the probable risk with a degree of confidence on the elements necessary for an effective petroleum system. If all you have is a structural map, what is the risk for reservoir, source, seal, timing? And those are absolutely critical in a highly competitive system.
It completely changed the way we began to think about things, and you could be very predictive about it.
It's one of the few approaches, maybe the only approach I'm aware of, that allows you to be predictive about all the elements of a petroleum system. For example, predicting reservoir, predicting seal, predicting trap, and predicting source rock. We have done this in many places in the world, and it is truly a predictive technique.
I've also had to note that there have been two kind of sequence stratigraphy wears two hats. One is age prediction, where people focus on the cycle chart, the sea level curves. And the other is lithologic prediction, where people focus on the evolution of depositional systems through time and space. And while the cycle chart has been the subject of much debate and to some extent challenged because of the imprecision of dating techniques, the evolution of depositional systems and prediction of lithologies in time and space has been, in a sense, more robust or not as challenged. Recognizing that there are countless variations on the theme, the fundamental aspect of sequence stratigraphy is that it is a set of rules. It isn't a single model, and those who apply it as a model are probably going to have some issues. Those who apply it as a set of rules will find that the approach works in all depositional settings.
My first big learning is that it's an integration exercise. So you need to make sense of all of the data, and it's basically the scientific method, right? So your first interpretation is a hypothesis, and the only thing you know that you're wrong, you just don't know where. And then you start to integrate more and more data to test that hypothesis, and then when your interpretation explains that data, and then you're ready to do prediction, right? Mm-hmm. So keep testing that until you get an interpretation that actually fits, that can explain all the data.
So we call it stratigraphic forecasting. If I'm working my way up a 1D section, what do I expect to see next? And you start to understand what the facies in the system are. What's the deepest water facies? What's the shallowest? Where's your tidal flats or things that might indicate a shoreline? And you come across that and say, this is what should come next. Oops. If it's not there, it helps point your eyes toward looking at a contact, or is there a significant surface in there of erosion or non-deposition, some high-yield surface, and maybe we become better predictors of what's going on up and down that wellbore, because it's an interpretive process.
For me, it's a kind of a tool. It's a framework to put all your observation into a coherent framework. It's really kind of a way of thinking, or a tool to put your observation in, a tool to kind of organize all your little local process you can see there and there. And if you're dealing with things like, I deal a lot with outcrop that are continuous, so it's easy. But if you're dealing with a well here and a well here, and maybe a crappy seismic line in the middle, then that becomes a very powerful tool to predict what's happening in between and make some prediction about what kind of facies, what kind of architecture you might see.
I think the main use in industry is the facies, because then you could predict if you were in the deep water, you could see channels and canyons and all those sort of things. Up on the shelf, you could see incised valleys, you could see prograding deltas building out and things like that, that could be then tied into an individual cycle of deposition from one sequence boundary to the next, and you could then tie the whole thing together from sort of stem to stern.
Here we are at an oil company, and this is some of the fundamental research that we do, and it's because what we do is it's prediction. We need to take what we see, okay, and predict and interpret away from data control, and that's really the fundamental job that I have as a stratigrapher working for an oil company.
So the sequence stratigraphy allowed me to lay down layer after layer after layer, get pretty much instantaneous heating of an area, instantaneous movement of oil or gas to the relevant highs, and then looking at the relationship of the highs from one to the other and how they spill the oil and gas.
The evolution of sequence stratigraphy has been interesting to observe. We started out with seismic data. We gradually spread into outcrop and core and well log.
But the pathway in both of them for the future, I think, is increasing integration of multiple data sets. If you've got a well that you can correlate to a record section, you've got a calibration for both depositional facies, porosity, permeability, and age if you do an adequate job on getting the fossil record out of it. The exact same thing applies to the outcrop. Where is your stratigraphic section that's a Rosetta Stone? Do you have enough calibration of the age that you can take that and project it over a geographic area? And have you properly analyzed the depositional facies based on sedimentology and geochemistry? If you do that full integration at either scale, the outcrop scale or at the regional basin scale, you have a competitive edge.
I had done my PhD work out in the Guadalupe Mountains, and after 5 years at Exxon doing research in sequence strat, I went back to the Guadalupe Mountains with my old advisor on a field trip. His name is Lloyd Prey, and he took us over to the western escarpment of the Guadalupes, where these huge erosional unconformities and deep water deposits were exposed. And it was all at the seismic scale. And so when I saw that, I said, oh, we can apply this to the outcrop. The outcrop actually shows this.
It allows you to do something besides correlate. And so when I started in the oil industry in 1982, we used to correlate logs. So you take some well logs and you look for similar patterns and you connect them. So, gee, that shore face looks like that shore face, looks like that shore face. Those must be the same. And you connect this, because the well log signature is the same. They even look the same in cores when you had them. So you connect them. And what was happening quite often is you were connecting things that had a similar depositional environment, but they weren't synchronous. So they were time transgressive units of some kind. And so the power of sequence stratigraphy is being able to put the architecture into place that is the time component of that and not the lithologic component only. So you leave log correlation behind and you start to interpret.
Everything that Peter Vail did actually started from strong well ties, and then everything went from there. So that's when he came up with the seismic reflections follow timelines. Is because after trying to tie wells and out of his frustration of formation boundaries not conforming to seismic reflections. So and then what we saw is that that seismic reflection actually were following a paleo slope. So that's when he came up with the seismic reflection follow timelines, not formation boundaries. What actually for me was the big revolution.
If you want to determine what has happened in sequence stratigraphy, how else would you explore those basins which are under water depths down to 10,000 feet if you didn't use seismic? So the advancement of seismic became extremely important, and along with that, then in the drilling of those type basins, you had to have whole new drilling systems, production systems, and identification of what was reservoir and what wasn't reservoir in the petroleum system. So sequence stratigraphy played the important role in promoting the technology that was used in that phase of 40 years of exploration and 31 new producing basins, creating billions of dollars worth of wealth and multi-million barrels of oil reserves.
People normally are really quick on telling the data is poor quality, and actually the method, the seismic stratigraphic method, really push you to go deeper and challenge that. And what I joke with my students is that a seismic stratigrapher need to push the data so badly that you need to make the geophysicist uncomfortable.
We still come back to seismic data because it is the only continuous imaging of the subsurface that we have. All other data tend to involve leaps of faith between wells, between cores, between outcrops. But seismic data gives us continuous imaging, and now with 3D seismic data, we have 3D imaging of entire systems. And some of these 3D volumes are incredibly large. We stitch together multiple surveys. We're getting a much bigger picture, a much bigger view of the world. So our window to the world is expanding and allowing us to refine how we interpret in a sequence stratigraphic context.
One of the things we're starting to do a lot the last, I would say maybe the last 5-10 years, that will probably carry on even more in the next decades, is we used to do a lot of 2D, pseudo 3D stratigraphy, but now we were talking about the Norfolk Shelf of Australia, where you have lots of data available, 3D seismic, something like that. And you can start thinking about what's really happening in the 3D point of view. So not only shoreline to shelf to margin to basin, but then along strike variability. I think that's where we're going to see a lot of things that might not fit the traditional model, or that's going to challenge our thinking.
Who would have thought back in the days of 2D what the explosion of 3D data would do, and you can get a whole matrix of data and cut it any way you want to and slice it and vertically and so forth. And then the application of computer workstations and that to the 3D, who would have thought that what came out of that, nobody could have predicted that. And then the next thing, everybody's drilling shales now, and can sequence stratigraphy be applied to shales? Can you look at the deep water deposition or of shales to predict which are going to fracture best, or which are the richest in hydrocarbons? I think that's a whole new field that.
At that time, that was sort of the great holy war, the great jihad in source rocks. There was one group that said it was all about anoxia and preservation. The other group that said it was all about production, and you had to make it first, which of course you did. And then the interesting thing about sequence stratigraphy really pointed out there was a third variable, which was dilution, which was a much bigger factor than either production or preservation, because you can pour dirt in a lot faster than you can grow algae.
There again, we find you can apply the same concepts that are used for sandstone and carbonate reservoirs. They are applicable to shales as well. Most of the shales appear to be within a sequence stratigraphic framework. You would call them condensed sections. And you can see these condensed sections. You can see the basal, they often are sitting atop an unconformity, and you can see that unconformity. You can place the shale itself normally within a transgressive high stand system of tracks framework. And what we have also found is that we can, once we have established the sequence stratigraphic framework in an area, that we can place other important properties within that framework so that we can map out these other important properties. And what I mean by the important properties are things like geomechanical properties and geochemistry, which are main drivers for doing exploration and development for unconventional resource shales.
In terms of where are the next opportunities, so much of what we do in stratigraphy in general is we observe what happened, and even with sequence stratigraphy, it's based on observations. We see certain patterns in the rocks, and from that we make inferences to how that actually occurred. And really, I think one of the real opportunities in stratigraphy, that one thing that we're actually focusing on at Chevron, is actually being able to model how that occurred. And one approach we're taking is sort of a physics-based approach. Is if we can actually, look at, we understand the physics quite well. And if we look at changing different dynamic parameters of the system, the subsidence, the sediment supply, the conditions under which the sediments are formed, can we actually replicate what we see in the rock record? And that's really what's been advancing so far. Is it's a very observationally based, and from those observations we've made inferences and predictions from them. But I see the real future opportunity is, can we actually validate that? And that's something that we're very much involved in here, is actually trying to go that next step in terms of prediction.
The conceptual advances and the computing power and the experimental advances have made it now possible to do forward models. So we can actually go from the kinds of flows we have to sort of modeling what rocks might be formed. So I think that's a big one. So we can sort of take the forward modeling approach and use that within the stratigraphic framework. Sequence stratigraphy kicks in to sort of populate at the smaller scale. So, because sequence stratigraphy, the way we do it now, is wonderful, is perfect. It works just fine for exploration scale problems, or understanding things at kind of the basin scale to sub-basin scale. But if now you're talking about a field scale or a particular part of a depositional system, you need to go beyond that.
I think basically the future has to be simply quantifying everything more. So we've got to get basically our time scales, we've got to get our rocks with reasonable time scales sorted out. So applying everything that's going on in zircon geochronology to this also, ideal. You know, the integration of these things. We've got to get the rates of change, and the only way to do that is to get better timing on rock packages.
Well, I think one of the things that's evolving in our science is this idea of source-to-sink analysis, that learning something about the hinterland allows you to be predictive about the depositional sink. So integrating those two concepts, source-to-sink and sequence stratigraphy, will really empower both of these. You know, sequence stratigraphy is all about understanding the sink, the depositional basin, whereas source-to-sink looks into the hinterland, the uplifted areas where sediment comes from. So marrying those two together, I think, will be a really step change in our understanding of how depositional systems really work. You know, big rivers produce big fans, and you can't argue with that.
Sequence stratigraphy is now providing a great template to source-to-sink. They're giving time-constrained intervals, for example. So it's ideal to use stratigraphic sequences well defined like that in source-to-sink. Source-to-sink at present is still fairly immature and diffuse, but using stratigraphic sequences and their geometric elements within source-to-sink is a good way to proceed, actually.
And of course you're going to see variations, you're going to see modifications. Pete, I was always interested in, Pete would give a paper and someone would stand up and criticize it very widely, and perhaps rightly so, because Pete would think about it, and pretty soon the things that he had been criticized for was built into his story. So.
I mean, sometimes people get lost in the weeds. You know, are the models perfect? Far from it. Okay. Do they explain a lot of what you see? Most definitely. And there's still questions, you know, are Earth's surfaces truly time synchronous? You know, within the resolution of what we work, they appear to be very close, you know, and they give us a really strong framework within which to describe rock.
There is no silver bullet for the answers to science, you know, but at least people are willing to step out there and put new ideas out there and new methodologies and new approaches out there. There's part of it is going to be wrong. Somebody's always going to sit down in a physical model in a flume for their PhD and say, I don't think rivers respond this way, you know. So they're always going to pick things apart. But there's always going to be a modicum of, you know, truth and opportunity and methodology in what people put out there. And so, you know, younger people need to be able to glean out the good and not throw the baby out with the bathwater, right? So there was a lot of good things that came out of this group of people who were willing to sort of put themselves out there with new methodologies and new ideas, knowing that it wasn't going to be the complete answer, but that there was going to be a part of advancing the science was going to lie in those new ideas.
And it's proven very effective. in the world of oil and gas. And I guess the greatest testimony to its usefulness is the fact that people vote with their feet. And it has been embraced by the geologic community. And so, like it or not, I mean, you can argue against it, you can poke holes in it, but the vast majority of earth scientists have found it to be a useful approach to basin analysis and stratigraphic prediction.
If there's a better method, I'd love to see it, okay? And it has to be something that can be reproduced and done.
In fact, I took Bob Mitchum and Pete Vale to Last Chance Canyon after we had done a lot of work. And Bob climbed up the hill and we looked across and saw the big prograding high stand and the onlap of the low stand. And Bob turned to me and he said, "You know, Rick, we were right."
Imprint is there and it's held up remarkably well, I think, during the last few years, all these years up till now, and that as long as you put in the proper interpretations of the sequences, get the dates, get the sequence boundaries and all that, then it is robust, no matter how old it is.